This is a podcast for Unit 2 in AP Chemistry, and Unit 2 is about chemical bonding. So this is going to be notes for day 1. We're going to talk a little bit about some stuff that goes along with chemical bonding. So I'm going to start out with states of matter. All matter has two distinct characteristics. It has mass and it occupies space. The properties associated with the three states of matter and the behaviors of the particles that make them up are summarized below. So there's solids, and there's liquids, and there's gases. And solids have definite shape and volume. The particles are packed tightly together and only vibrate gently around fixed positions. So here they are, nice and tight together. Liquids have no shape, take the shape of their container. Would be no definite shape there, and they have definite volume. The particles are free to move about. Gases, neither definite shape nor volume. The particles spread apart, filling all the space in the container available to them. Solids. They fall broadly into two categories. Crystalline, where a regular, ordered, repeatable 3D structure of particles is found. Or amorphous, where the arrangement of particles is not regular or ordered. However, in both cases, the particles in the solid have very little energy and move very little in relation to the whole. Liquids. Like solids, liquids have particles that are very close together, but unlike solids, the particles in liquids are constantly moving and colliding with one another, having significantly greater energy and move a lot in relation to one another. Since solids and liquids tend to have their particles very close together, their volumes are often very similar. Since in a gas, the particles possess enough energy to overcome any intermolecular means between the molecules, like between one water molecule and another water molecule, any intermolecular forces, and hence move around completely freely and with large spaces between them. A liquid represents particles in an intermediate state between the extremely ordered and low energy state of a solid and the extremely disordered and high energy state of a gas. The properties of solids and liquids. All of the properties of solids and liquids, such as viscosity, surface tension, hardness, etc., are dependent upon how the particles that make up the solid or the liquid are arranged, and the extent of the attractions between those particles. For example, a liquid where the particles are attracted to one another with very strong interparticular forces is likely to be more viscous than one where the force of attraction is weaker. So viscous may be a new word to you. I like to think of molasses or syrup for pancakes as viscous. It's a little bit thicker and it's a little bit slower to perhaps maybe fall down a board at an angle if you were to have a race of liquids. Heating and cooling curves. Since the different states of matter have particles with differing energies, converting between them requires a change in energy. The changes in energy associated with phase changes can be quantified in heating and cooling. Gases and KMT. KMT stands for kinetic molecular theory. Gases are made up of particles that have relatively large amounts of energy. A gas has no definite shape or volume and will expand to fill as much space as possible. As a result of the large amount of empty space in a volume of gas, gases are easily compressed. Pressure. A pressure is exerted when the gas particles collide with the walls of any container it is held in. Pressure can be measured in a number of units, for example, atmospheres, millimeters of mercury, or torr. So 1 atmosphere is the pressure at sea level, and that is the same as 760 millimeters of mercury, which is the same as 760 torr, which is short for Torricelli. Kinetic molecular theory. The kinetic molecular theory is the basis for properties of gases. The 5 postulates are: 1. Gases are composed of tiny particles, atoms or molecules, whose size is negligible compared to the average distance between them. This means that the volume of the actual individual particles in a gas can be assumed to be negligible compared to the volume of the container, and therefore the total volume that the gas fills is almost all empty space. The observation that gases are compressible agrees with the assumption that the actual gas particles have a small volume compared to the total volume. Example, the volume of the container. 2. The gas particles move randomly in straight lines in all directions and at various speeds. 3. The forces of attraction or repulsion between two gas particles are negligible, except for when they collide. 4. When particles collide with one another, the collisions are elastic, means no kinetic energy is lost. For example, like when a pool ball hits another pool ball, there is energy lost in that. The collisions with the walls of the container create the gas pressure. Elastic collisions agree with the observation that gases, when left alone in a container, do not seem to lose energy and do not spontaneously convert to the liquid. 5. The average kinetic energy of a molecule is proportional to the Kelvin temperature, and as a result, all calculations involving gases should be carried out with temperatures converted to Kelvin. Using Kelvin eliminates the problem of negative temperatures leading to negative energies and negative volumes, etc. These assumptions do have limitations. For example, gases can be liquefied if cooled enough. This means real gas particles do attract one another to some extent. Otherwise, the particles would never stick to one another and therefore never condense to form a liquid. Gas laws. We covered the gas laws in first-year chemistry. We talked about Boyle's law, Charles' law, Avogadro's, Gay-Lussac, and the ideal gas law. Ultimately, you need to know that PV equals nRT, PIV-NERT. You can get all the other equations from that one. So if you have a P1 and a V1, on this side, these are assumed to be the twos, so to speak, but if you bring them over here, they're the ones. And bringing them over there, I mean by dividing by it. So pressure and volume have an inverse relationship. It's a negatively sloped line. So if pressure goes up, volume goes down. Pressure and temperature have a direct relationship, a positively sloped line. So if the pressure increases, the temperature increases. One to note, Avogadro's law. At constant temperature and pressure, volume is directly proportional to the number of moles of gas present. The volume of a gas increases with increasing number of moles and vice versa. So more junk in your trunk, you got an increase in volume. Helpful. So we went over this in first-year chemistry. A lot of the AP Chem tests would like you to derive some of these, but sometimes I think if you just memorize certain chunks, you can get pretty far with it, and it frees up time and working memory. So pressure times volume equals mass, which would have to be in grams, times R, which is the universal gas constant right there, times temperature, which has to be in kelvins, because the universal gas constant has kelvins in it, divided by mm, which is molar mass. Molar mass is from the periodic table. You could rearrange that, and you'd get molar mass equals density times R times T divided by P. And I have a really strange way of remembering this. Molar mass equals dirty P. Just remember P comes out the bottom. Partial pressures. So the total pressure of a system is the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, etc. And note that these P's here, P1, 2, 3, are really equal to N, which is the total number of moles of gas present, times RT divided by V. So Boyle's law, if you increase the pressure, the volume decreases. So if you decrease the pressure, you have more volume. Charles' law is a direct relationship. So as the temperature goes up, note these are negative numbers. Temperature is increasing, hence the volume increases. And this one is Charles' law with temperature in Kelvin. Again, as you increase your temperature, your volume's going up. So think of a balloon in your house, your air-conditioned house that is cold, and you take it outside and it's hot. The volume in there will expand if it's hotter outside than inside. Or if you bring a balloon from the store outside and it's cold, it will shrink. Dalton's law of partial pressures. Dalton's law states that in a mixture of ideal gases, the total pressure exerted by the mixture is equal to the sum of the individual partial pressures of each gas. So again, pressure total is P1, 2, and 3. And those individual P's could be calculated using this and plugged in there, and this could also equal the total P. That is the end of the notes for that section.